The great progress of cold spray equipment and process development during the past 2 decades has been accompanied by impressive improvements on the ancillary side, namely robotic automation. Automation is key for extended industrial deployment of cold spray also outside the well-established sectors of military and aerospace applications. Automation is not only required for serial production. It is also necessary for achieving accuracy and reliable quality in customized manufacturing or repair. The hassle, as SB3D put it, with automated cold spray production is mainly the robotic programming. In fact, the leap from producing test sample geometries towards programming cold spray runs for industrial coding, 3D printing or joining applications may be huge. In the laboratory, it is often sufficient to produce a chunk of good material and shape it by subtractive machining. The accuracy demands to robotic calibration are moderate in this case, and the kinematic programs are, more or less, easily written at the shop floor. Once a cold spray procedure has been developed to the point where material quality meets specification, the transfer from test coupons to a potentially complex workpiece shape may emerge as a bottleneck. We have encountered cases where the demand for cost-prohibitive programming eventually hindered the process from arriving at the shop floor. Cold spray requires to code areas line-wise, while keeping standoff distance, lead and tilt angles within a narrow process window. This property imposes constraints on the feasible tool path and may result in complicated robotic moves. NX can automatically generate the toolpath from a CAD model. Let us look over Aline's shoulder for 5 minutes to see how easily this is accomplished. She begins with setting up the cam session.
The latter comprises a digital model of the machine, including its kinematics and the post-processing. In our case, we use a KUKA KR60 6-axis industry robot combined with an external axis, a positioner with a rotary plate. After the CAD model of a workpiece has been added to the cam session, it is placed in the preferred position by applying suitable constraints. Thus, turbine plate and its support are stacked in the center of the positioner table. In order to calculate paths along which the tool is to be moved, affected surfaces and guide curves need to be defined. The selection of surfaces is possible by different methods, such as specifying single surfaces or tangential surfaces. To allow for correct tool movement, ensure positive orientation of all contiguous surfaces by picking the correct orientation of their normal vectors outward. As for surface selection, there are various possibilities to select the guide curves. Moreover, curve manifolds can be defined. Again, attention needs to be paid to select the appropriate curve orientation. Beyond the tangential traversing speed, the cold spray process typically requires full control of the accompanying tripod along the entire tool path. NX-CAM allows for separate specification of local lead and tilt angles with respect to the local surface normal. These angles can be set in the multi-axis deposition module and the freeform additive coding section. Once the surfaces, guide curves and tools have been selected, the path properties can be determined. The triering strategy needs to be defined in accordance with the given component shape and the surface topology. In our example, the surface region to be coded is homeomorphic to a cylinder surface. The spray tool is to be moved primarily in the circumferential direction around the airfoil. Secondarily, it is to move in vertical direction following either a helical line or a vertical stack of tracks, each alternating in direction. Further parameters having to be set comprise basic coating properties such as the single path thickness and total layer thickness, the path start and end points, path overhangs, and geodesic path separation distances. Finally, specify the order in which the paths are to be generated. The ordering scheme can vary between surface regions. Once all settings have been made, the path is calculated and visualized in almost no time, allowing the user to verify the result. Arrival and departure paths, as well as transfer moves between separate path segments or surface regions, are determined by means of non-cutting moves. Complex surface shapes sometimes require combinations of several tool pathways. NXCam allows for generation of separate paths, for example, one along the plate airfoil and another on the adjacent platform surface, which subsequently can be linked by appropriate transfer pathways. After the toolpath programming has been completed, it needs to be specified how the robot should drive the tool along the path. In NXCam, this can be done using the robotic rules. The robot needs to know how to orient the tool during the coding process and which axis configuration to use for positioning the tool. Also, the approach and departure positions, the orientation of the external axis, as well as motion speeds and motion types need to be set. Movement instructions to choose from comprise point-to-point movements and linear path movements. Point-to-point commands generate black box direct movements toward the goal position, with the robot choosing the fastest possible way. On the contrary, linear path movements ensure that the tooltip moves along a straight line, with position deviations within a defined tolerance range anywhere. The approach and departure positions at the beginning and end of the coding process respectively are reached by point-to-point movements, whereas the tool path across the coding region and the transfer paths are traversed at varying locally defined speeds with narrow position tolerance as defined by linear path movements. All settings can be visualized, checked and edited in the robot control interface. The tooltip trajectory thus is a polygon approximation of smooth coding paths embedded to the component surface. The integrated simulation module supports final assessment of the programming result. When the simulated tool motion looks right, the post-process can be started. Eventually, the NX post-output file can be uploaded to the controller of the real machine tool. Then, the manufacturing process is ready to run on wheel. The NX library provides a set of different post-processors. Using the post configurator, existing post-processors can be edited or new post-processors can be created and implemented in NXCam.
The generic NX animation is a pure kinematic visualization of the toolpath geometry, which does not capture the motion speed. Several machine parameters defining the kinetic capability of the KUKA robot are not included in this simulation. Therefore, the timing of certain moves is unrealistic. The true robot motion results from combination of the true machine parameters with the output of the NX post-processor for the KUKA robot language KRL. Details of approximate positioning or flyby motions, for instance, cannot be predicted at this level by NX. To obtain a realistic machine simulation, the KRL code produced by NX could be executed virtually in the vendor software KUKA Sim Pro. An alternative workflow is possible when Xenomeric with the extension RunMyRobot is used as motion controller. The package offers the advantage that an NX program for a spray process can still run on the robot after recalibration or minor tool changes. Xenomeric takes standard NC commands as input, which are obtained as output from the NX post processor. A realistic machine simulation is provided by the virtual xenomeric machine VNCK. It is integrated in NX and enables a seamless workflow from toolpath generation to process run simulation. We show a little example in the following.
In this use case, a repair task is to be accomplished using cold spray. There is a groove located on the cylinder surface. The side walls of the groove are inclined at a 70-degree angle relative to the surface normal of the cylinder. This V-groove shape requires a certain toolpath strategy, considering the local surface inclination to evenly fill the groove with repair material. A spiral movement of the cold spray nozzle around the cylindric component presents a suitable driving strategy. The starting point for the repair process is placed in the center of the groove because they are the steepest and requires the most material, that is, the most repetitions of the deposition path. Starting from this point, the tool is moved on a helix-shaped path. The first winding is in upward direction. 2 windings in downward direction follow. Then 3 windings in upward direction, and so on. Following this pattern, additional windings are iteratively programmed until the tool traverses the groove completely from the top to the bottom. The relevant workpiece surfaces need to be assigned to each winding according to their position. Then, all windings need to be linked with one another so that a connected tool guide regarding the groove is generated. A spiral path that repeatedly crosses the center of the groove and is extended outwards by 1 winding distance before each turning point. Since all tool speeds and orientations with respect to the workpiece surface and all applicable robot rules are already set, the simulation can be started now. At first, we run the NX toolpath simulation, which is helpful to visualize the deposition of sprayed material in the V-groove. The motion timing of this animation is not necessarily realistic, but the sprayed track is. At this point we stop the toolpath simulation and switch to the machine code-based simulation by the VNCK virtual machine. VNCK opens a virtual user interface of the xenomeric. Xenomeric manages all available tools such as different cold spray nozzles, powder injectors, and stagnation chamber extensions. The tool selection has been made in the early stage of toolpath programming. It is only reviewed here but not altered. Now we can start a realistic process simulation including all auxiliary moves. Bottom left we see the machine code line currently executed. Next to it we see the axis position and velocities. On the right hand side the tooltip motion speed is continuously displayed.
In our laboratory in Berlin, we run the 13-axis system shown on the right-hand side. On the photograph, 2 cold spray torches were mounted on the 2 6-axis Comao robots, and a workpiece is mounted on the 13th axis. The installation shown here serves for development of multi-axis operated additive manufacturing or local repair processes. To control the robotic motion, we use NX-CAM. It calculates the tool path from the CAD model and passes the motion commands directly to the xenomeric controller of the Comao robots. This connection allows for offline programming of the kinematics and circumvents potential difficulties arising at the interface between a robot's command language and the output of a CAM system. The Siemens software yields a complete tool chain. As an example of net-shape additive manufacturing, we show an existing 3D printing process for copper in the mirror of NX-CAM simulation. Along the spray path, the nozzle maintains constant standoff distance, constant tangential speed, and piecewise constant lateral tilt angles. The productive spray path remains of pairs of rails. Frequent repetition of the shown motion pattern makes the rails grow in height. Hereby, they form vertical walls with a flat top. The resulting cross-section shape is rectangular, with slightly rounded corners and an aspect ratio greater than unity. The tilt angle specification, in connection with uniform rail separation, is crucial for the net shape obtained. On the cold spray process control side, Siemens technology has developed a gas flow monitoring system allowing real-time detection of nozzle clogging. This system allows observation of flow corruption in an early stage, before it manifests by receding particle velocities compromising the quality of the workpiece. Nozzle clogging occurs when spraying certain metal powder materials at elevated gas temperatures. The phenomenon is the catastrophic end of a long-lasting process which commences imperceptibly. Powder particles randomly striking the nozzle wall in the divergent section little by little form an internal coating, gradually increasing the wall roughness. The roughness continues to grow in a stochastic manner until few nucleation sites form which efficiently capture impinging particles at increasing rates. Some of those material pile-ups may erode subsequently, but eventually one of them will block a significant portion of the cross-section area. None of the proceedings can be sensed by the cold spray system control until the choking cross-section diminishes due to massive blocking. The changes take place in the supersonic section of the flow, from where no information can propagate backwards to the stagnation chamber where the temperature and pressure sensors are located. Nevertheless, the particle velocity at the nozzle exit starts to decrease well before the final clogging. When the nozzle wall ceases from being hydraulic smooth, the internal boundary layer grows, dissipation increases, and the effective expansion ratio drops. Transient changes of the flow direction may occur. Continuous observation of the after-nozzle flow by the Siemens monitoring system reveals such erratic flow periods, signalizing imminent clogging well before particle velocity drop becomes critical to part quality. The system recommends when to shut down the cold spray system for nozzle change. It helps to exhaust the operation span of the nozzle by indicating the right moment to stop spraying. In addition to this flow monitoring system, Siemens technology has developed inexpensive refurbishment procedures for clogged nozzles. The careful removal of debris makes it possible to reuse the nozzle. In combination, the two technologies render cold spray productive, reliable, and affordable, even when using feedstock with pronounced clogging tendency. Although today's presentation puts some emphasis on kinematic programming, the recipe for success in industrial cold spray application lists a few more ingredients. Our experience with cold spray helps to create a cost-efficient workflow at the shop floor and to assure permanent quality of both the process and the product. Siemens Technology is active in R&D of cold spray since 2005. Potential applications of cold spray have been evaluated technically and assessed cost-wise. Owing to the unusual diversity of Siemens' product portfolio during the past 15 years, we ran projects related to power generation, transmission and switching, electrical machines, oil and gas, or steel making. After having conducted 80 cold spray projects at Siemens, it is common to us to learn our customers' language and thinking. In most cases, cold spray competes with qualified procedures. Any expected advantage needs to be balanced out with the risk of introducing a new technology and supply chain. In response to this challenge, we pursue agile collaboration with our customers, joining forces of the domain specialists and the cold spray experts. We thank for your kind attention and look forward to getting to know your thoughts.